Hey guys, so today we're going to be doing a torque equilibrium question, and in this video the question is asking us what is the minimum value of x for which the pole will not slip on the floor. And it's important to note that x is referring to the distance between a 200 kilogram hanging mass to the top of the pole. And another important thing about this question is that there is a rope that is exerting a tension force that is holding the rod upright. Okay, so you can go ahead and pause the video now in order to try to solve it for yourself, and then come back when you've finished. Okay, so two things that we know about the pole that are useful in any torque equilibrium question is that the net force is equal to 0 and the net torque is equal to 0. Okay, so why might these be true? Well, we know that this pole is in equilibrium because it has not slipped yet. So that means that there must be no net force on the pole, because otherwise the pole would accelerate in the direction of that force, because force equals ma. And similarly, there must be no torque on the pole, no net torque, because otherwise the pole would rotate. And one thing about this torque concept is that you can calculate torque over any point on the pole, and because we know that the pole is not rotating in any direction, and the torque over any point that you calculate must be equal to 0. So let me try to explain that a bit better. So I could calculate the torque over this point on the pole, and because the pole is not falling down this way or going around that way, we know that the torque over this point must be equal to 0. And similarly, I can calculate torque over this point on the pole, and because the pole is not going this way or going up that way, the torque over this point must be equal to 0. Because if there were net torque over this point, or any point, the pole would rotate around that point. Okay, so now let's move on to this first part, that the net force is equal to 0. So let's draw a free body diagram of all the forces on the pole. So we know that there's going to be the force of gravity downwards, and this is the combined force from the 200 kilogram hanging mass and from the center of mass of the pole. And we know that this rope is going to pull the pole to the left. So there must be a tension force to the left. And I don't have any information about how big this tension force is, so I don't really know which line is longer, so I'll just draw it like this. So because the net force is 0, there must be some force upwards. And that's going to be the normal force from the ground. And notice that this normal force must have the same magnitude as the force of gravity, because otherwise the pole would move in the upwards direction. And similarly for tension, there must be some pull going to the right, some force going to the right, that causes the net force to be 0. And that's going to be the force of friction. No other force can be to the right here. So through this free body diagram, we know that the normal force is the same magnitude as the force of gravity, and that the friction force is going to the right. So let's draw that. Okay, nice. Now, let's draw all these forces from where they're acting on the pole, and this will help us later. So I'll just draw that here. So if I have my pole here, I know that the tension force is going from the top of the pole, and I'll just draw the ground. The normal force is going upwards from the ground. There's a force of gravity from the middle of the pole and from wherever the mass will be. And there's also a friction force that we know must be to the right. Okay, so if we're thinking of all these forces, the normal force, friction, gravity, I'll write it out, and tension, one of these forces we have no information about, and that's the tension force. So in order to make this question doable, we need to eliminate it from the problem. And when we're calculating the torque over some point, we're going to choose a point that makes the torque done by tension 0. And you can think for a bit of where that point may be. And this might help you. Remember that torque, oh that's a very bad torque, equals force times r perpendicular. So if a force was this way, the radius would have to be perpendicular to the force. Okay, so we're going to calculate the torque over this point. And that's because the r perpendicular of tension from where the force is coming to the torque is 0. So this tension force is going to do 0 torque, and we can remove it from the question. Alright, so now let's think about this point, what direction each force does torque. So let's start with the normal force. Which way would the normal force make the pole want to rotate? Well, you can think about somebody pushing the pole from downwards, and it's going to make it want to rotate like this, over the point. And gravity, you can think about it, would make it want to go like this, or in the opposite direction. And the friction will pull the pole this way and make it want to rotate like this. So it's also going to be working with gravity in this direction. And because the net torque must be 0 over any point, we can equate the torque done by friction, the torque done by gravity, to the torque done by the normal force. Okay, so let's do that. So, torque done by the normal force, which is force, normal force, times r perpendicular. And we know that this whole rod is 5 meters. I'll show here. The whole rod is 5 meters. So the r perpendicular is going to be 5 cosine 70. So this line right here is 5 times cosine 70. And that's just geometry. So normal force times 5 cosine 70 equals the torque done by the other side. So there's some torque done by the center of mass, which is going to be 15 times 9.8, or the force, times 2.5 cosine 70. And it's 2.5 because it's being acted from the center of the pole, plus the torque done by the hanging mass, which is similar to this, 200 times 9.8 times x cosine 70. And this is the changing variable. And we have the last torque, which is done by friction. So it's going to be the force of friction times 5 sine 70. And the reason why it's sine is because friction is doing force to the right. So F perpendicular is going to be upwards. And it's going to go all the way to the top. And this length is 5 sine 70. Okay, so what do we know about... So from the question we know that our variable has to be x. But as we see, we have this force of friction, which is the normal force times the coefficient of static friction, and we have this normal force. So really, we have another variable that's a normal force. So how can we figure out how much a normal force is? Well, look at this free body diagram. The normal force is the same magnitude as the force of gravity. So the normal force must be the total weight of the rod plus the hanging mass, which is 215 times 9.8. So I can plug those variables in. So 215 times 9.8 instead of normal force times cosine 70. Hey guys, so I'm going to use the power of editing to fix a mistake I made in my video. So in my video, I wrote that the torque done by the normal force is 215 times 9.8 times cosine 70, when in reality, I forgot to multiply this by 5. Because r perpendicular is 5 times cosine 70, as I wrote here, and not just cosine 70. And don't worry, the answer that I get in the video is still correct, because when calculating the answer, I used the correct numbers. Okay, I hope you enjoy the rest of the video. Equals 15, and this I already wrote, so I'll just do dot 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 dot, plus the force of friction, which is 215 times 9.8 times the coefficient of static friction times 0.3, right, because this is normal force times the coefficient of static friction, times our perpendicular, which is 5 sine 70. And we solve for x, and we get that x is 0.757 meters. Okay, and there's one last thing that I should explain that you might be confused about. And that is, why did I choose the normal force times the coefficient of static friction for the force done by friction? After all, static friction can do zero force. If something is stationary and there's friction on the floor, static friction will do zero force. Static friction does as much force as it needs to do. Well, the reason why I chose this is because this is the maximum static friction force. Right? The normal force times the coefficient of static friction is the maximum force that the friction can do. And the reason why I want the maximum force is because as x decreases, which is what the question is asking us, what is the minimum value for x, the force of friction must increase. So, I'm making x be as small as possible by making the force of friction be as big as possible, which is the normal force times the coefficient of static friction. So, when I plug in this maximum friction force, I'll get the minimum x, which is 0.757 meters. Okay, so I hope that is clear, and thank you for watching the video.